Hi. In the last video, we've stumbled upon the complex root case that we couldn't deal with because we don't know anything about imaginary and complex numbers that we actually require in order to deal with this issue. But this is why we're going to start by defining what imaginary and complex numbers are. So let's start with imaginary numbers. To be perfectly honest, we just need to have one imaginary number. And we're going to denote it as I. And I is defined as square root of -1. Do we know how much is it? No, we don't. So from this moment on, we're simply assuming that square root of -1 is some number I. And look, this is actually sufficient for us to deal with the case of a square root of any negative number. If we've got square root of -9, this is the same as square root of 9 times -1, right? Which in turn is the same as 3 times 3 square root times -1, or simply we can write it as 3i. And look, we can do it with any number. Square root of -2 is the same as square root of 2 times square root of -1. So this is square root of 2 times I. And look, now we're able to deal with square roots out of any negative number we want. What we're gonna do is to take I out of the root to make it real inside. Okay. Now, how about complex numbers? Look, because imaginary numbers are imaginary, in order to bring them to the real world, we're combining them with real numbers. And generally, the structure of a complex number looks like this. This is h plus minus some v times I. Why construction like this? We will get to it. Let me just give you some examples. So complex number could work like 8 plus 4i. This is one complex numbers. Those two do not appear separately. Those appear together. Or we can have 7 minus 2i. This is also a complex number. Okay, look, complex numbers are good. It's good to see complex numbers on something called Argand diagram. Okay. This is a specific diagram that has two different types of axes. One is imaginary axis, and the other one is real axis. So, if we've got a complex number, we can divide it into 2 parts. One part of the number is going to be an imaginary part, like this part over here, and the other one, the real part, right? This is the real number. Okay, so how do we put a number like this? Look, let's just say that our number is some h plus v, right? Okay, and so let's just say that from this moment on, every time when we talk about v, we will use green color, and when we talk about h, we're going to be using yellow color. So h is the real part of a number, v is associated with an imaginary part of a number. Okay, so let's just say that this number, that the location on this is given by distance h over here on the real axis, and v on the imaginary axis. Okay, so now look, we got a pair of points over here of a complex number, one that is h and one that is v. And look, right away we can see that if I'm gonna draw a line from the origin, then this line is going to be associated with the angle theta and a vector, or let's simply a line going from origin to C. What is the length of this vector? Well, we know that this size is h. This size is v. So using Pythagoras theorem, we can calculate that if this is going to be called r, like radius maybe, it's going to be equal to h squared plus v squared and taking square root out of it. And look, this is actually a real number. What is more, it's a non-negative number. In a sense that here we have two squares, so we must have two positive numbers, right? So because those are the real numbers h and v, and we got a square root. Okay, so this vector that you see over here, r, we're going to call radius vector. And I hope just by looking at this Argand diagram, you see that there must be some specific connection between real part, imaginary part of a number, the radius, and of course, the angle of the radius vector. Okay, so I hope that what I showed you reminds you just a little bit some stuff that you already did in high school. But before we go and connect complex numbers with some things you know from high school very well, let's get for a second back to our main topic. Our main topic is, of course, solving second-order differential equation with constant coefficient and constant term, where we encountered now an issue associated with complex numbers. So, we've got a case where, case 3, right? And in case 3, case of complex roots, we had equation y is plus a1 y prime plus a2y equals to 0. That is all we need for now. And what case do we have here? What if it turns out that a1 squared is lower than 4a2, which of course we remember implies that a1 squared minus 4a2 is smaller than 0. Look, we know that the solution to the characteristic equation is given as negative a1 negative a1 plus minus square root out of a1 square minus 4a2 over 2. But look, over here we clearly see that here what we have is a negative number, right? We know that this expression is lower than 0, right? So we couldn't take the root out. But now, with imaginary numbers, we finally got the tools that will actually allow us to do just that. How? Okay, thing is very simple. If I'm going to take negative 1 out of here, right? So, if I'm going to take minus 1, I'm going to have expression like this. Right? Because if I'm going to take minus out, the expressions will change their order, and of course now they are positive. However, I know also that instead of square root of negative 1, I just can't write I, right? So, now, what we get over here is actually a complex number. This number over here will look like h plus minus vi. However, we will have 2 over here. 2 complex numbers. This is why we're going to call them, which color I'm not using this one. It's going to be, we are going to be calling those conjugate complex numbers. Why conjugate complex numbers? Because they appear to you as a pair, right? R1 and R2. So the two solutions, and each of these solutions will have some real and imaginary part, but they will be conjugated with each other because they're related in a way, right? And look, we clearly see that in our example, simply the real part of a number, of this conjugate number, h, is given by negative a1 over 2. Well, v is given by 4a2 minus a1 squared over 2. Okay, so now we know that if we have complex root case, we can deal with it if we're going to use imaginary number. But okay, before we before we move on, let's just do one example to clear everything. Okay, let's just say that we've got a case of r squared. So characteristic equation already, r squared plus r plus 4 equals to 0. Okay, so what we're gonna, what can we do with this characteristic equation? Okay, first we notice that a1 is equal to 1, so a1 squared is equal to 1. a2 is equal to 4, which means that 4a2 is equal to 16. So clearly a1 squared is lower than 4a2. So we have a case of complex roots. So in order to find their values, we just apply the regular formula with the twist, which by the twist I mean this I in the end. So we've got, this is negative a1 plus minus 4a2 minus a1 squared over 2. Okay, so we get that this is simply negative 1 plus minus 16 minus 1, which is square root of 15, and of course we cannot forget about I. Okay, and look, we can rewrite it right away in the form 1, negative 1 over 2, right? Plus, minus, square root of 15 over 2. We could simplify this, but it's not that important. Because it wouldn't help to actually make this expression simple. And we see that this part over here is the real part. It is our h. Well, this is our v, which we once add and once subtract. Okay, but look, this leads us to an expression for a complementary function, right? Even with what we know from here and using what we've learned before, we can find that we can write an expression for complementary function, which is a1 e to the power r1 t plus a2 e to the power r2 t, right? So now that we know the solutions, how about we substitute, right? So we go, instead of this we write a1 e to the power h plus vi times t, right? Plus a2 e to the power h minus vi times t. But look, both of those expressions have common part, right? This e to the power of h. I should do it with yellow color, so okay. And so why not take it out of the parentheses? So we got that this is e to the power of h times a1 e to the power vi plus a2 e to the power negative vi. And this is a very nice expression for the complementary function. However, even though if we've got h, we know what to do with this part, it might be rather troublesome to deal with those two, right? How much is e to the power some number times imaginary number? So how much is e to the imaginary power? Well, the answer itself might surprise you. And remember, during dynamic economic analysis, we talked a lot about exponential functions, especially with e, natural exponential function. So how much is, I told you that if you take e to any real power, you can get a very, very big number or a very, very small number, but you can never get to 0. And definitely you cannot get a negative outcome. But those are imaginary numbers, they are no longer real, so maybe the same rules do not apply. Maybe we need to try a different approach. Actually, an approach that will allow us to make sense how it looks. Because at this moment, I doubt that we could use anything that we've used in mathematics, introduction to economic analysis, or dynamic economic analysis to deal with this very bizarre case. And for this reason, to deal with this case, we need to connect our deliberations on imaginary and complex numbers with circular functions. Actually, just the two are important to us, but I will tell you a little bit about other things. Okay, so imagine that this is a circle, perfect circle, because it should be. However, this is the best I could do without the circular. Okay, and now remember the Argand's diagram, right? Now let's imagine that this circle has a radius r, right? And now here in yellow we've got real part of a number, and here we've got v associated with the imaginary part. Now look, they are all, the size of the radius over here depends on h and v, right? Because we said the radius is h squared plus v squared square root, right? It's just simply the distance. You calculate it out of the Pythagoras theorem. Okay, now, how is the sine function defined? Of course, sine for our angle theta over here. Well, sine is v, right? Divided by the radius, and we remember that radius is h squared plus v squared square root. And in this, by similar token, cosine is h divided by r. Those are, those relationships when you take different sides of the right angle triangle, and here we've got adjacent. We've got a side that is adjacent to to our angle. Well, here is the one that we've got right in front of it. Those are the definitions you also considered probably in length in high school. But look, let's connect those definitions with what we get over here. And look, let's start with the sine function. Okay, and look, imagine that we start with this at this point. Look, at this point, what happens? R is equal to 1. Okay. R is equal. Okay, R is equal to R always, but V, as you see over here, when we start at this moment, is at 0, right? So let's put here on the graph where we increase value of theta over here. And look, what is going to happen as R moves up? Look, we would see that at the beginning, V is getting bigger and bigger and bigger and bigger, right? So we would expect that V is, as we will move in that direction, the V is going to be getting higher and higher and higher and higher and higher. And look, until we get to the point B. What happens in this point? In this point, V is exactly the same size as R. So then, if V and R are of the same size, then V divided by R are equal to 1. Okay, now I see that I need to fix this a little bit because this picture is going to be too small. Okay, P over pi over 2 pi. Okay, let's put here 3 over 2 pi and 2 pi. Okay. Now, I hope you know from mathematics that here we've got 90 degrees, but those are, 90 degrees expressed in radians. Those are expressed when you go from degrees to radians. It amounts to half a pi, right? Because pi is when we go over here. So from that, I hope you can see that we get that here V is getting bigger and bigger and bigger and bigger until it reaches the top of 1 when we are at 90 degrees or pi over 2. What happens next? Well, if we move forward, so we move counterclockwise, what happens is that now look, our V is going to be getting smaller and smaller and smaller, and smaller and smaller until it reaches 0 after we moved by a pi. And I hope now you know where I'm going with this. Then V is becoming negative until the moment when we are here and V is equal to -1. And then it starts growing again, right? Because we are still moving counterclockwise here until we get to 0. And look, now if we're gonna move again over the circle, this shape is gonna repeat. And of course, if you would move in the opposite direction, we would get this. And look, this is how we get the sine function. This is how sine function is related to circle, and how is it related to complex number, to v in our case. And look, we can do the same thing with h. And look, what is happening over here? Look, if we start at this point, you see that h is the same size as the radius. So we start at 1. Okay, let me just also fix this, because this is too small. Okay, and it's going to be pi. Somewhere over here is going to be 3 over 2 pi. Here is going to be 2 pi. Okay? And then, what happens? Look, as we go higher and higher, h is going to get smaller and smaller and smaller and smaller, right? Right after here. Then h is going to turn over here. But look, here we have positive numbers, 0. Here we have negative numbers. So h is going to go down. Then it's going to be still negative. I'm sorry. It's still going to be negative, but it's going to be getting bigger and bigger and bigger. And finally, it's going to become positive again. It's going to be getting bigger and bigger and bigger until we arrive at this point. And now, we've made the full circle. Every time we repeat the circle, the shape is repeating. And of course, if we go in the opposite direction, the opposite happens. Okay, and look, now we've made a small revision of circular functions. How do they work, right? Now, what I want to remind you here is that, look, the values taken by sine and cosine are bounded by plus and minus 1. And now it makes perfect sense, because look, v at most can be as big as r, right? And then it's equal to 1, or at the lowest it can be equal to negative 1, right? And then we have the bottom. And the same goes for h. So both of these functions have the same amplitude. Look, the only difference between them is that they are moved in the phase. Look, if I would move sine to the left by half a pi, I would get cosine. If I would move cosine by half a pi to the right, I would get sine. Okay, now we get a gist of how sine and cosine functions work. So now that we know that, let's review some properties of sine and cosine functions that are going to be crucial to us in our future derivations. Okay. So, property, oh, you know what? Before we go to properties, one more thing, tangent and cotangent, right? Tangent, lambda, theta, tangent theta is defined as the ratio of sine theta to cosine theta. But look, just by looking over here, we see that this is v over r multiplied by r over h, because we divide, so we multiply by the reciprocal. Those two cancel each other out. This is nothing more than v over h, and in this case, h cannot be equal to 0. And cotangent is cosine theta divided by sine theta, and it's equal to, of course, the reciprocal to this, h over v, where v must be different than 0. Okay, but now let's go to properties of sine and cosine. Okay, let's review just those, the most simple ones. Look, we got that sine lambda plus 2 pi n is equal to theta, of course, not lambda, sine theta, and so this is, let's call it property number 1, and cosine theta plus 2 pi n is equal to cosine theta. Of course, assuming that n is an integer. Okay, so look, what first property is telling us is that those functions are cyclical. They actually repeat themselves every cycle. Look, what you see over here is that every 2 pi we're going to have full circle. And because if we're going to have full circle every full pi, every full 2 pi, this function is simply repetitive. Okay, then let's go to property number 2. Another one that we actually discussed already, and this is the one that says that cosine theta is equal to sine of theta plus pi over 2. So look, those two functions have the same amplitude, they are just different in phase. Phase means when they go up and when they go down. Basically, what we see over here is when we move cosine to the right by half a pi, we'll just get the sine function. Or if we move sine by half a pi to the left, we are getting cosine. Okay, so now property number 3 is that cosine negative theta is equal cosine of theta. Okay, and sine negative theta is equal to negative sine theta. Okay, this property is simply telling us that cosine is a function that is a mirror reflection of itself with respect to vertical axis. You see, we got the same shape the further we go from 0. But as you see, this property is not true for the sine function. Okay, then property number 4 is something you should remember from high school. Sine squared theta plus cosine squared theta is equal to 1. Okay, and so we've got just 2 more. Just 2 more. We're going to be using them a little bit later, but just once. Just once. Okay, so we've got that property number 5. And so we've got that sine theta 1. So now we've got plus minus theta 2 is equal to sine theta 1 times sine theta 2 plus minus cosine theta 1 cosine theta 2. Oh, I'm sorry. sine, here cosine, here here must be sine and cosine. Sorry, like that. And the second one is the cosine of theta 1 plus theta 2 is equal to cosine theta 1 times cosine theta 2 minus plus sine theta 1 sine theta 2. You don't need to know these by heart. We're just gonna use them once when we're gonna be dealing with complex roots a little bit later. But let's put them all down so we remember what we're gonna refer to. Okay, and look, this is the end for this video. But before we finish, I just want to I just want to tell you about one crucial thing that we're going to use in the next video. And those are the derivatives. Because it turns out that we're not going to be proving it, but derivative with respect to theta of sine theta is simply equal to cosine theta. And derivative of cosine theta is equal to derivative to negative sine theta. And those two, I would like you to know by heart. And please remember those watching the next video, because those two results, so those two values of those two derivatives are key to understanding the next step. Unfortunately, I already had to erase, but just look at the graphs and it makes perfect sense. Look, you will see, remember, derivative measures the slope of the function. And it's amazing to see that actually the slope of sine is given by cosine. And the slope of cosine is given by minus sine. Okay, so this is it for the introductory information. In the next video, we're going to move to Euler's relations that are going to be crucial to understanding the complementary function in the second order differential equation. Okay, thank you for your attention and see you in the next video.